Yeah, I'm Elliot. Hi. I'm also from Edinburgh, as everyone is. So Aretha are some of my supervisors. And so last Friday, I gave a talk on history matching. Is that, and, oh yeah, Ken's there too. Am I amplified? Okay. Maybe it's the way the acoustic thing. Anyway, yeah, so last Friday I gave a talk on history matching, which is like the idea behind my whole PhD. And today we're going to look at one specific aspect of it, which Tell Ming has just introduced, so that Gaussian process emulation and how we can do that better. Okay, so first I'm going to do a very, very quick overview of history matching. I know I'm not going to bore anyone too much, who was there on Friday. Just to introduce why we want to look at Gaussian process emulation and what that actually means, and then how we can then introduce ideas from high-dimensional numerical integration, like Willy Monte Carlo, to Gaussian process emulation to maybe do it better, and then time allowing, maybe see how we can apply this to a DDE problem, which we should be quite familiar with by now. Okay, history matching, what is it? So it's a way of treating inverse problems. So we have the function, we have some observations about the function, we can only take point-wise evaluations of this function, and we assume that our data is recreated by the function evaluated at the true parameter value, and we then add some noise. So the two main methods of doing this, of solving an inverse problem, is optimization. So optimization is when you're trying to find these are exactly. So a point estimate, you can do Bayesian inference, which is what Tell Ming is doing. So that's when you're trying to attach a whole probability distribution to your whole parameter space for finding good, find the most probable key to solve. And then history matching is slightly different. So history matching is when we want to instead find a set. So in terms of complexity, it kind of sits in the middle, but unlike optimization, we still do have some uncertainty information, which is why it's still good. And it's especially used in situations where x is very high, so our dimension is very high, and our function is usually some kind of compute simulator, so usually involves solving some PDEs or something, so it's very expensive. That's really the context. So don't worry too much about understanding what this means. This is just when we are doing history matching with Gaussian processes, which is pretty much what everyone always does. This is how we define our set or intermediate set. So it's all the features in our, all the parameters in our parameter space, such that the implausibility lowers the threshold. When we define the implausibility like that, don't worry about understanding that's fine. But what's happening is just we're fitting some Gaussian process to data, and in this case, our data is the evaluation of our function. And then on the right here, we can see our implausibility function. And these lines represent different thresholds, so different alphas. So if we take this alpha here, then the set that we get is the set that is given when this implausibility function is below this threshold. So that'll just be that interval there. Of course, this is only in one dimension, and we're interested in when this gets to much higher dimension where things get a bit more difficult. If you don't take anything else away from this, the main thing to look at is this mean function here. So this is the mean function of the Gaussian process, the Gaussian process emulator. And essentially, our history matching is better, the better emulators we can build. What does better mean? We'll talk about it in a second. But from this point on, all we need to know is that we want to build good emulators. Okay, so what is an emulator? So fortunately, Tell Ming has explained this quite well, so very high level. But an emulator, a Gaussian process emulator, I mean, you can think of it as the exact same thing as Gaussian process regression. I'd say the context is slightly different, maybe. But regression is more general, emulation is where we are trying to emulate some expensive function. And that also means that we get to choose where our points are, so where we put our data, because we can evaluate the function wherever we like. So as Channing said, we start with a prior, so we have a prior mean function, and we choose our covariance kernel. We then introduce data, which is our function being evaluated at different parameter values, d to I. And then we update our Gaussian process with this data with a likelihood function, and this is all conjugate, so this gives us a closed form expression for our posterior mean function and our posterior covariance. But today, all we need to worry about is this posterior mean function, which is also, as Chairman said, this is deterministic. This is just essentially this is just kernel interpolation. So we do know what this function is. So although Gaussian process is stochastic, everything that we're doing today is deterministic. Well, it doesn't. It can be deterministic. So when I say we want to build a good emulator, what I mean is we want to use our mean function as an approximation for our true function. And therefore, by a good emulator in this context, what I mean is reducing this error, so the L2 error between our mean function and our true function. Okay, so what can we do? What can we change to make our emulator better? What tools can we play with? So one thing we can play with is our experimental design. So essentially how we choose these beta i's in our Gaussian process. That's one thing we can play with. And the other thing we can play with are our kernels. So not only the type of kernel we use, but also the hyperparameters involved with them. Technically, we can also look at the prior mean function. We can change that, but we're not going to look into that. In general, that doesn't really make as much of a difference as we think in theory. Untested. Okay, so now with our two tools that we can play around with, what underlying structure of a problem can we exploit using our two tools here to get better convergence rates? Well, the thing we're going to be looking at is anisotropy in the simulators. So what I mean by this is when the inputs have different levels of importance. So this can be from two different meanings, two different sources. So you can know this a priori. So depending, if you have a lot of information about the model that you're using, for example, if it's a PDE, and you know something about it, then you may already know that these inputs are right. And so we can use that. And then, yeah, so we can use that as when it comes to our building our emulators to build better emulators. Or if you don't really know, also in the context of history matching, most of the time we're doing this for very, very complicated simulators. And a lot of people that I've spoken to really don't know a priori a lot about how important their parameters are. So what you can do is do a PCA afterwards or a global sensitivity analysis to get some idea about how important your different inputs are. Certainly in the high dimensional situation, it's very likely or very standard that the importance of your inputs are going to be quite different. That's just anecdotal. Okay, so that's the idea of Gaussian process emulation and what we're trying to do. But we're going to introduce this idea of QMC, which is used in high dimensional integration, and see how we can then apply this to Gaussian process emulation. So this is going to be very quick revision on Monte Carlo method. I'm sure we're all familiar. So the Monte Carlo method, we just want to integrate functions of this form over this domain. And we can approximate our function, our integral, using this Monte Carlo method, where we're just taking function evaluation at certain parameter values in this case, and these parameters are chosen to be completely random within the state. When we measure the integration errors, the different integration error will be in this case. It can be shown that this is of order n to the minus half. So that means that if you double the number of samples, then your integration error reduces by a factor of √2, for example. And the real takeaway from this is that this is independent of dimension. So this is why it's really useful in high dimensional integration, because this is true no matter what S is. But QMC takes that one step further. So it's the exact same problem. So we have the same equal weight rule for our integral approximation. And instead of choosing these our these i's randomly now, we pick them according to this rule. So I mean, I don't know if anyone's familiar with this, but it's not so important that we understand what's going on here. But our theta i's, so our I parameter value is then given by I over n, where n is the number of samples that you want in total, multiplied by a generating vector. And then this bracket notation means that you just hit the fractional part, which means that we are staying in the unit square. So that means that all your points are just going to be in the unit square. And then this random shift here, this is this just moves your design a bit and keeps it within the unit square. This is maybe more for the convergence proof, and in practice may not be so necessary to do that. And then the result of this is that for suitable function, and, yeah.
So that is independent of I. So you shift the whole.
Yes.
By, okay.
Yes. It's not I. So the whole thing gets shifted. So it is still this very structured lattice. So I'll show you a picture in a second. For suitable function F, I'll talk about in a second, and for corresponding appropriate generating vectors there, also talk about the integration error can be shown to approach arbitrarily close to order n to the minus 1. So this is significantly better than our standard Monte Carlo approach. Okay, so what do we mean by suitable function? So by suitable function, there's smoothness constraint and you need bounds on your derivative. And there also needs to be a degree of anisotropy there, which is where this idea comes in. So we choose our generating vector to be, I'm going to explain it. We choose our generating vector to be optimal for integrating functions within the reproducing kernel space, where the reproducing kernel of this space is given by this kernel here. That's a lot of words. If you're not familiar with it, then don't worry. All that you need to know is that this reproducing kernel space is very similar to a Sobolev space, which is why we really like this kernel. And also, in this kernel, we have these weights, gamma j, in which we can encode the anisotropy within our function space. So in this case, we can choose appropriate weights depending on the degree of anisotropy that we think is present in our function f. And then these weights can get very complicated depending on how complicated your function is, but we're going to keep it very simple now. So we're just going to be using product weights, which is the simplest kind of weight. I won't explain what that means really. And throughout the rest of this presentation, the weights will be as such. So gamma j equals 1 over j squared, where j is the dimension. So the first dimension has a weight of 1, the second dimension has a weight of 1/4, a 9th, so on and so on. And so that's how we're including that anisotropy. It's also worth noting that with QMC, we need our weights to decay. So we can see that this is a decay rate there. There's quite a lot of room to maneuver in terms of how fast it decays, but it does have to decay. So you do have to have, I can get this. You do want that, something like that on the left-hand side. That's quite important for this to work. Okay. That's the last bit. So that's what it looks like. This is without the shift. But so in 2 dimensions, we have the structure, and we can see how, based on how we're choosing these weights, how each dimension is weighted slightly differently. There we go. So that's what our design will look like. So now we're going to try a test problem. So very naively, the first thing we're going to do is we're going to choose our function to be a random realization of our QMC kernel. So that's the kernel that we use to generate our generating vector. So we know for sure that this function exhibits this same anisotropy that our kernel will, and therefore our design point to do. So we know that for this function, it should work. Measuring the integrations like this, as we said before, and we can see that in 2 dimensions. The top line there, the top blue line, you can see, I'm not sure you can see very well, is top line is our Monte Carlo estimate for the integral, so we can see that this is decaying. So this line here is order n to the minus 1/2, so we can see that that's approaching that. And with GMC, we're getting order n to the minus 1, which is what we'd expect, which is great. How high the line lies doesn't matter so much, it's just the slope that we're looking at. And then when we go in high dimension, we can see that the Monte Carlo estimate can be weird, but we can see that it's still roughly order n to the minus a half in Monte Carlo. And we can see very clearly that our QMC estimate is still order n to the minus 1, even though we're in 100 dimensions. So this is completely dimension independent, which is why I like it. Okay, so that's QMC for integration. That's a quick crash course on that. Can we apply these same principles to Gaussian principles emulation? Same function, it's that same problem, except now, instead of trying to integrate this function, we are trying to approximate it with the mean function of our Gaussian process. As I said before, this is a completely deterministic function. And it really depends only on our choice of kernel and our design points. So trying to do this, now we're doing our approximation error, which is the alpha error that we saw before. And so, as we said, we're going to use our experimental design, which are our QMC points here, with the generating vector generated from that same kernel. So we know that the degree of anisotropy is the same. But also, as I said, we have to worry about the kernel as well. So we do happen to have a kernel that we know encodes the same anisotropy. That's what we're going to use. We're going to use this QMC kernel for the covariance kernel within a Gaussian process. Now, this kernel is really weird. It's non-stationary, it behaves very strangely. In terms of the kernel interpolant, which is what our mean function is right now, that's not so bad. But when we're trying to apply this to a Gaussian process, the meaning of what the covariance is with this kernel kind of leaves the building. I don't quite understand what that would mean. But this is what we're going to try first time, just to see if our ideas work. Okay, so on the left-hand side, we have a similar idea to what we did initially with the integration. So on the top line there, the blue line, that is our Monte Carlo error. So what we're doing there is we're choosing Monte Carlo points, so random points in space, and we're choosing an isotropic kernel. So we're including no anisotropy in this problem in that kernel interpolant at all. And then on the line below, we have our QMC interpolant, so anisotropic points in our lattice rule design, and our QMC kernel of the covariance kernel. But this isn't very convincing at this point. We see that they have the same decay rate, but this is in 2 dimensions, and that's what we'd expect in 2 dimensions. What happens when we increase the dimension? The QMC is better. That's great. So, so yeah, we can see that very quickly our isotropic kernel becomes really quite bad, and our QMC kernel actually interpolant does actually get a bit worse. So we can see on the left-hand side, they're both doing order n to the minus 1, which is actually really good. We can see our QMC kernel is doing a bit worse, but when we really push the dimensions, when we get to 1,000 here, we can see our isotropic kernel is it's almost constant on this graph. It's really bad. But we notice, once again, anecdotally, that our QMC kernel interpolant kind of decays to order n to the minus a half and then stays there. It doesn't get any worse than that.
Which is the
Which
is the
generating vector. Yeah. So the generating vector is generated from the same reproducing kernel Hilbert space that is with the kernel that we're using for the covariance structure here.
So it's also weighted.
It's also weighted. So yeah, there are 2 things going on here. The 2 differences. The points are weighted and the kernel is weighted.
Sorry,
the points are, we changed the design so that the points are weighted in dimension somehow. So in some sense, you can think that more points along the more important dimension and less along the less important. And we're also changing the kernel as well. So the kernel is also nice.
And the difference between the orange and the red is post MC and the different kernel.
Yes.
You have results when you have an MC and the same kernel.
Yes. 1 second. Well, I'm glad you have that, because that is what I wanted to say. So, okay, but also there's a slight maybe conflict of interest here in that we're using the same kernel to generate the function as we are to generate in the covariance structure. So maybe there's something untoward going on there. So instead, we're going to now try and use the separable exponential kernel. So this looks like this. So So this is a very standard kernel that's used in statistics, because this kernel has a much more convincing interpretation of all the covariance instructions after using it. And also we do have in this separable kernel length scale parameter that is equivalent to a weighting of each dimension. So we can, in this lambda j, we can encode how important each dimension is. And the question is, how does lambda j and so our kernel weights, length scale parameter here, and how our QMC weights, how do they relate to each other? Using some numerical experiments, we found this kind of relationship. This seems to work quite well. This is not a proper thing, but it's good. It seems to work. And then, so using this relationship here, do we get a similar thing? Yeah, we get pretty much the exact same thing. So we know that this wasn't a property of this QMC kernel. We know that this is entirely coming from this anisotropy that we've induced there. Okay, so that's that. And now back to Al's question. We changed two things. Which one has the largest effect? So here I'm doing that what Al says. So I'm using Monte Carlo points with anisotropic kernels, Monte Carlo points with isotropic kernels, QMC points with isotropic kernel, and QMC with anisotropic kernel. And you can see that it does seem like pretty much all the gain is coming from using the kernel, and not so much the design point. I've been thinking about this a lot. This is a very fresh result, and I think it's the few things going on behind the scenes here, which I think can explain a lot of this behavior. And I do think that the design is still important, but at least initially looking at this graph, it does seem like all this gain is coming from changing the kernel. Okay, so I don't probably have some time. Okay, so very quickly, I'm going to take this idea and I'm going to apply it to our PDE problem. So we've seen this a few times now. We have our PDE model, as Anastasia just said. So we're modeling ground flow in Mexico, I think. New Mexico, that's where the data is from. That's not important. So
it's kind of even square domain. It's something.
New Mexico is kind of square. But I thought it's a good approximation. So we have our random field here, which represents our hydraulic conductivity field, and we have our pressure field that we get. So our pressure is our pollution, and we get different pressures. So in the context of Nimbus problem, we're going to have readings about our pressure field, and we want to infer what the correct random hydraulic, no, the correct field hydraulic conductivity field is that would give these pressure readings. And we have the same boundary conditions as Anastasia did, I think, for someone. I assume she should do it for me. So we're going to model the random field slightly different. We're going to be using the reverse expansion. So, I mean, technically, we're kind of abusing this a bit because we shouldn't really be using these weights for the KL expansion, but it does seem to work. In the future, we change how we do this slightly so that it marries better. But essentially, if we're modeling this random field as a log normal random field, and then we are expanding it in this KL expansion. And then our parameters for inference then become this theta here. So this vector, this random vector, and we truncate it to S. That's that. And then as a product of doing this, we know that all of these are, so we have our random variable times by our eigenfunction and the square root of an eigenvalue. And these eigenvalues then give an idea of how important each parameter will be because they decay. So we know that our first parameter, when ordered properly, the most important by far, and then it decays this way. And it's also decayed like 1 over j squared, so that's convenient. And we also know that this decay rate does propagate through the PDE into the solution. It's very important. There's a lot of mass in that I didn't do. Which type of parameter for Oh, I don't know. I think I'm using 0.4 in both directions. It's either 0.4 or 1. So yeah, there's lots of modeling going on here, but I'm not so interested in that. I just want to see if we can recreate our problem. And then this is a function that I'm going to emulate. So I'm going to directly emulate the sort of like surface there. So I'm directly emulating the top of our implausibility function, which is like the numerical approximation to our pressure field given a value of our parameters, and then taking the distance between that and some real life observations we have, which is also a slightly useful to see because it really only works with linear functionals, but let's not worry about it. So this is what we had with the test function. We saw this kind of pattern here. What do we have for our PDE? That's the same thing. That's good. So this is just a product of using our test function here. We can see that this is actually doing something here. We are exploiting the anisotropy inherent to the PDE problem. And as a result, this should be quite generalizable to any problem where there is a clear, distinct decay in the importance of each input parameter. Yeah, so that's everything I have to say today. So for conclusion, history matching is great. We should all use it. And it uses Gaussian process emulation to solve inverse problems. We can use tools from high-dimensional integral approximation to try and improve our Gaussian process emulators. Gaussian is fast grids here. I didn't talk about that, but that's also of interest. And then finally, the full takeaway from our last plots are the kernels seem to be the most important thing. So when you're doing Gaussian process regression, choose your kernel style. Thanks.
Questions?
So coming back to my question. So I was expecting that you choosing the kernel would give you convergence rather than constant time.
Yeah.
But what I was surprised by is that QMC is not giving you a better rate 1/n.
Yeah.
You know, an idea why.
Well, I think the theory only shows that it should be 1/n to the minus half. Right? I think, but...
Yeah, I mean, you go back to your definition of the error, the two and then cosine. Yeah. So it mainly comes from the fact that for QMC, you get a rate of 1/n for this integral, and then you still get the square root. That's where you get the square root.
And then why would you not get for NC for 1/the square root n?
We don't have any theory for
So in the end, we don't do this integration. It's the only for the time. Yeah, no, I understand. So I think that's more. And there's not here, but it is
no.
Oh, okay,
I have some theory.
But then my point is that you expect the QMC to have better convergence rate than the current integration problems. And I guess the hope was that for experimental design, you also have better rates.
Yeah.
But clearly you're showing in your experiments that even for one dimension, we're seeing the same rate. And then for higher dimensions, you're seeing also the same.
So
for 2 dimensions.
Yeah, we were surprised. So this is just integration here. Is that what you mean?
Yeah, but you're seeing the same rate for the carbon QMC.
For 2 dimensions. I'm going to say this is an input question. Yeah, we are. So what's surprising with this is that it's so good in the beginning. So we weren't expected to get n to the minus 1 straight away. I mean, in your kernels, you are imposing a lot of structure onto your problem. So we think that's why it's so good initially. You are in the kernel. So Monte Carlo here, by Monte Carlo, I mean, So if it, the kernels are not the same.
The kernels are not the same.
No, but I just need to remember what it actually is. The kernels here are isotropic.
Yeah.
Yeah. But no, so the kernel for the top one is isotropic, for the bottom one is anisotropic.
Yeah, that's what I mean.
Okay. Sorry.
But then the convergence rate of Monte Carlo you can see are the same.
For 2 dimensions.
For 2 dimensions.
Yeah.
So even for 2 dimensions, you'd expect
a bit of a gain.
A bit of a gain.
Yeah. You don't see it. But I mean, this is just the numerical result, so I can't.
That's what I'm saying.
So that is quite surprising that you don't see much of a gain. So also, the anisotropy really kicks in later dimensions. So obviously, we would expect to see it get much better. What is surprising is that N2 you don't see any gains yet. I agree.
I think it's really because it's really 2 very different problems. Think about integration, it's really only the points that matter. But once you move to the interpolation setting and doing it first process emulation, the basis functions really play a crucial role, and those are kind of independent of the points. So there's extra dimension that's coming in that seems to be a lot more important, and that is independent of how you choose the points. So that in that sense, the difference is really the kernel, and then you don't see that much difference.
But also, do you know if there's any theory about the 1/n rate or Monte Carlo? As I recall, there's a sport about diffusion. But he does have some like this squares information. And he does see the 1/square root of n. Which is why it's trying to see 1/n Monte Carlo and also 1/5 minutes. I heard the 1/square root of n comes from that Monte Carlo.
Yeah, it also does seem like as you go higher, it does seem to be 1/square root of n seems to be the case to this. So that seems to be the fundamental thing.
Yeah.
I think this early gain isn't really explained well, I think. So yeah, that is a surprise to us.
So yeah, I mean that one there are good questions here that I really quite intrigued with. Okay. And there are the questions here that I'm quite intrigued about. Is that why are you saying 1/n?
Yeah.
For low dimension.
And
the second is 1/square root of n expected what wasn't.
I believe the last is true.
Basis for this consistency.
If you use higher order QMC rules, you should be able to get faster convergence. So
yeah, that's also true. This is only rank 1. Yeah.
thank you again.
Thank you.